Hello everyone! Welcome back to my class. Our topic for today is the Chinese Remainder Theorem. Before we start, let's have some important information about the Chinese Remainder Theorem. Are you familiar with this theorem? How did it start? Who discovered this theorem? Hmm, let's have a quick background on the Chinese Remainder Theorem. Let's find this out now. The Chinese Remainder Theorem is the fundamental tool that allows us to combine congruences to reach conclusions about the original problem, or let's say solve systems of simultaneous linear congruence. The idea first appears in the writings of the Chinese mathematician Sun Chu, who lived in the 3rd century. The method was further developed by Qin Shuxiao in the 13th century. In the West, Euler seems to have been the first to study it extensively. The method is fundamental and has numerous applications. Let's have this example. Find x such that 3x is congruent to 7 modulo 10. We will look for the value of x that gives us a remainder of 7 when divided by 10. Let's say x equals 9. Then 3 times 9 is 27. And 27 divide 10 is 2 remainder 7. Okay, so now we have 7 and 7. And so the value of x in 3x congruent to 7 modulo 10 is 9 and the congruence is 27 congruent to 7 modulo 10. We have here the Chinese remainder theorem. Let m sub 1, m sub 2 until m sub r be a collection of pairwise relatively prime integers. Two integers are relatively prime when there are no common factors other than 1. This means that no other integer could divide both numbers evenly. Two integers a and b are called relatively prime to each other if the GCD of a and b is equal to 1. For example, 7 and 20 are relatively prime because the GCD of 7 and 20 is 1. Going back to the theorem, the system of simultaneous congruences x congruent to a sub 1 modulo m sub 1, x congruent to a sub 2 modulo m sub 2 until x congruent to a sub r modulo m sub r has a unique solution modulo m equal to m sub 1 times m sub 2 until m sub r for any given integers a sub 1, a sub 2 until a sub r. Here's the proof of the Chinese remainder theorem. I'm giving you time to read and comprehend the theorem. Let's have this example. Use the Chinese remainder theorem to find an x such that x is congruent to 2 modulo 5, x congruent to 3 modulo 7, and x congruent to 10 modulo 11. So how do we solve this one? First, let's give the given. Where did we get 2 from A1? So A1 equals 2 from here, A sub 2 equals 3 from here, and A sub 3 equals 10, this one. And also the moduli. We have here m sub 1, which is 5, this one. M sub 2 is 7, this one. And m sub 3, 11, this one. Next, get the class modulo. How do we get it? We have to multiply them. M sub 1 times m sub 2 times m sub 3. We have the class modulo. 5 times 7 times 11 is 385. So now, we will use 385 as the new modulo. Then, we will substitute we will get the value for this one. M sub k equals the class modulo over m sub k. So first, the m sub 1 equals m over m sub 1 are the class modulo over the first modulo from the original equation, are the original congruents. We have 385 over 5 is 77. For m sub 2, we have 385 over the m sub 2, which is 7, which we will get 55. And for the m sub 3, we have 385 divide 11, 35. We will be using 77, 55, and 35 later on. The next step is to get the multiplicative inverse for each m sub k. So how do we get the multiplicative inverse? We have to have a remainder of 1. That's the goal for the multiplicative inverse, to get a remainder of 1. First, get the multiplicative inverse of 77 modulo 5. So 77 divide 5, we have now a remainder of 2 and the inverse of 2, modulo 5, we will find a number that when multiplied to 2 and divide to 5 will have a remainder of 1. Let's have 3. 2 times 3 is 6. Divide 5, we will get a remainder of 1. Therefore, the value for y sub 1 equals 3. How about the m sub 2? Inverse of 55, modulo 7. 55 divided by 7 is 7 remainder 6. So now we will use the inverse of 6 modulo 7. We will look for a number that when we multiply to 6 will have a remainder of 1 when divided by 7. We have here 6 times 6 is 36, near with 35 with a remainder of 1. Therefore, the value of y sub 2 is 6. The last one, m sub 3. We have the inverse of 35 modulo 11. 35 divided 11 is 3 remainder 2. Now get the inverse of 2 modulo 11. We will be using 6, which will happen to be 2 times 6 is 12, and 12 divided 11 is 1 remainder 1. Therefore, the value of y sub 3 is 6. So to get the value of x, we have to add the product of a sub 1, m sub 1, y sub 1, plus a sub 2, m sub 2, y sub 2, until a sub r, m sub r, y sub r. So, let's see. Since we have here these values, then we have x equals a sub 1, m sub 1, y sub 1, plus a sub 2, m sub 2, y sub 2, plus a sub 3, m sub 3, y sub 3, modulo 385. We will now substitute the values. We now get x equals 2 times 77 times 3 plus 3 times 55 times 6 plus 10 times 35 times 6 modulo 385. Then we have x equals 462 plus 990 plus 2100 modulo 385. We now have x equals 3552 modulo 385. We will divide 3552 by 385 and we will have a remainder of 87. Now, this will be the value of our x modulo 385. To check, we have to substitute x equals 87. We now have 87 congruent to 2 modulo 5. Let's try. 87 divide 5. Yes, it has a remainder of 2. How about 87 divide 7. 87 divided 7. Yes, we'll get now a remainder of 3. How about 87 divide 11? Okay, we now have a remainder of 10. And so, the value of x is correct. To get the value of x, we have to add the product of a sub 1, m sub 1, y sub 1, plus a sub 2, m sub 2, y sub 2, until a sub r, m sub r, y sub r. Since we already have these values from solving in the previous slides, then we will now substitute them. We now have x equals 1 times 105 times 1 plus 2 times 70 times 1 plus 3 times 42 times 3 plus 5 times 30 times 4 modulo 10, 210 rather. Then we have x equals 105 plus 140 plus 378 plus 600 modulo 210. We now have x equals 1223 modulo 210. We will divide 1223 by 210 and we will have a remainder of 173. Now, the value of our x is 173. Well, Let's check if it is correct. We will substitute the value of x into x congruent to 1 modulo 2, x congruent to 2 modulo 3, x congruent to 3 modulo 5, x congruent to 5 modulo 7. Substitute x equals 173. We have 173 is congruent to 1 modulo 2. 173 divide 2 has a remainder 1. Correct. 173 equals 2 modulo 3. 173 divide by 3 has a remainder of 2. Check. 173 divide 5 has a remainder of 3. And 173 congruent to 5 modulo 7. 173 divided 7 has a remainder of 5. Well, it is correct. That's the end of my lesson for today. See you again on my next class. Thank you for listening. For queries, just text or email me. Bye-bye.